Okay. So, hi folks, I'm gonna be talking with my teeth clenched as little as possible about a paper that was accepted to ICML 2022 on this topic that I've been recently trying to dig into, these dynamics in relatively simple neural networks, and trying to actually come up with sets of differential equations that describe how training behaves in the model. And there's a lot of promise in this kind of work. It helps us come up with more a robust idea of how training will change based on architectures and hyperparameters, but it also potentially gives us ways to start connecting deep learning theory with the differential equations that describe actual neuron firing and other kind of stuff. But it's all very rudimentary at this point. And this paper focuses on particularly dynamics in autoencoders, which we are all hopefully familiar with, but just as a quick refresher, we have a model which we have some input that we're trying to essentially reconstruct on the output. And this autoencoders operate under this bottleneck principle. They're one of the models that was, I believe, most informative with Tishby's work on information bottleneck, because you have a higher dimensional representation that you try to squeeze into a lower dimensional representation in the best way possible, so that that lower dimensional representation can reconstruct the full higher dimensional representation. So it's very similar to PCA in a lot of ways. Autoencoders are often described as nonlinear PCA under some constraints. VAEs are almost exactly described as nonlinear PCA.
Well, because when autoencoder is linear, it is PCA.
Yeah, exactly.
It's identical.
Yeah, so this is taking a step and looking
not
at.
entirely true. There's directions that it goes into that are similar to PCA, but it's not. It's a whole area where it's kind of like sometimes yes, sometimes no.
Yeah, so let's dive into this paper because they make a few claims about this, which I do want us to think about. So just at a high level, we'll look at these contributions, and I put exclamation points after these because they're all a little bit surprising. I mean, so like I mentioned in the beginning, the goal is to come up with these set of differential equations that exactly describe the training dynamics, how the loss is exactly decreasing. We want an equation where we can just analytically plot out that loss, and it should match exactly with what we get when we actually train. And we should also be able to come up with equations for the weights that exactly describe their trajectories in the weight space. So that's interesting, but exactly what this paper is trying to do. And for those of you who know Saxe's work, and we talked about it, I think now 2 years ago here in the reading group, Saxe's work on dynamics, it's a very similar kind of approach to what Saxe does. But the authors will eventually try to argue, using some of their analysis, that autoencoders do learn features of the data sequentially. So this is
the same as
exactly the same as what Saxe says. So this will, and this they extend this to say that under some constraints, even nonlinear autoencoders exactly learn the principal components, and they learn them in order, kind of, in the same way that Saxe describes in his paper. And I'll go into that background a little bit more in the next slide. They do make some other sort of claims about particular of particular interest, practical use for ReLU-based autoencoders. They say, I'm not going to talk about this too much. I honestly didn't dig into the details of it, but they claim that their analysis shows that training with biases is necessary for ReLU autoencoders. We can maybe look at that section in the paper if people are interested in talking about that. And they do a little bit of extension to actual real data, but it's only one data set, which made me very mad because we've gotten projected based on using only 2 data sets.
Can I ask something? Can I ask something? You said ReLU autoencoders and you said PCA components. To me, it seems like there is also largely they're linear and like they're piecewise linear. So it makes sense, right? If they PCA components in a way.
So well, we can talk a bit more about what constraints that they say it constructs PCs exactly.
Right. Like I understand that they use ReLUs. I know David Saxe also uses a lot of ReLUs because it's just easier to explain. But I feel like the PCA thing may be partly tied into the fact that they use ReLU. Because the work that I've seen where they say like, oh, it's not PCA for BAEs at least, sometimes it's like also different.
So I do think they also look into sigmoid activations
Okay.
and softmax,
Okay.
which does bring it a little bit away from ReLU, but the constraints that they put on SGD are a little bit different. They actually impose like a rotational symmetry constraint on
Okay.
SGD, which they claim gives them actual reconstruction of the PC. So we'll look at that though in more detail, because I think that is an interesting analysis. But to get into the background a bit, so this is just a very, very high level quick refresher on some of Saxe's work. So Saxe came up with a set of differential equations that describe the trajectories of the in the weight space for excuse me, for linear networks trained on regression tasks. And he came up with this. I think the most interesting story, which I took from that paper at least, is that you can analytically say that the network will actually one by one construct the dominant modes in the correlation matrix between the input and the output. Excuse me. So he had this like analytical measure that described his learning dominant modes, and the actual measures, even with nonlinear introduced nonlinearities, more or less displayed that. This is just a high level thing to take away from Saxe's work. There's a lot of detail in that original paper. I do encourage people to go back and read it because it's a great paper. It spawned off a lot of relevant work.
What is sigma? What is sigma again?
What is sigma?
Sigma 1,1, sigma 3,1.
Oh yeah, those are the covariance matrices. Sorry, I was looking for a lowercase sigma, and I was like, where? yeah, those are the covariance matrices. So this was so 3,1, I believe, is the input-output correlation or covariance rather. Sigma 1,1 is the input-to-input covariance, and
so sigma 1,1 is covariance of the input.
yeah, it's just between the different variables.
You can click on chat, it will disappear.
Yeah.
It's like it will be there blocking her. Like, can you use the mouse?
Oh.
Just click on chat. That's why I don't like when people post in chat. It just blocks our screen.
There needs to be a textbook dedicated to this topic. Apparently there is.
Okay, William, you got lucky.
Yeah, apparently, yeah, I'll need to look at what Alex posted to see that textbook, because that'll be interesting. And I think it's going to be funny in a few decades to see, if we do have a cohesive theory of deep learning, quote unquote, who's going to get credit, because there's a lot of different directions in that. This dynamics direction is, I think, a very small subset of the actual theory that's going into deep learning. I personally think it's a very important direction, but certainly not the only one. So I was kind of lazy in my slides, and I'm going to have us just kind of piece through the paper bit by bit, because it's actually quite simply structured, at least in terms of the flow of things. So we're looking at the dynamics in an autoencoder, right, where we have, and I originally put arrows in here, but I think they might have gotten deleted. But we have here, V is the weights on the decoder, I believe, and we have these weights W that are the weights in the encoder. And this is a bit of strange notation. Again, made me mad because I've gotten papers rejected for strange notation. And whoops. But here we have so this is just our, I believe you can just think of this as sort of the standard equation for an autoencoder. You have your encoder and your decoder, and you have your reconstructed input x hat.
This is really weird.
Yeah, it's very bizarre notation. It's, yeah.
I don't even think it's really, it almost doesn't seem correct, because I don't know if you could just represent an encoder as like a multiplication with image.
Yeah, it just looks like they're, yeah.
It looks like it's a vector.
Yeah.
Which it is, but this is only for one,
For one unit, and well, they are lambda k is just one hidden unit, and it's a linear. Lambda sum k is your activation.
I know, but it just seems like a really weird way of, I don't know, notating. I agree with.
I'm personally just not a fan of the notation. I don't know if I would have rejected the paper only on that grounds, as I've had people do to me, but it does, it just is funny. And here we're using the standard mean squared error, which is analogous to an energy function at the thermodynamic limit, whatever details. I don't think those are entirely relevant. But we're going to be using mean squared error here. So this is a bit where things begin to become kind of wonky for me. So the bulk of their analysis and the bulk of the paper rests on this simulated data, which is based on this spiked Weishart model. I'm not familiar with the details of the model, but I believe the idea is that you have some parameter sigma that is, this parameter chi, which is sampled from a Gaussian, and you can additively you can add this into some other this A matrix, and you can control these parameters somehow in order to get a bunch of different styles of inputs. I'm a little bit not familiar. Is anyone familiar with the Weishart model, or
is it Weishart or Wishart?
Wishart, I don't know. Say the German.
But the only thing I remember is that it's a conjugate prior for the Gaussian covariance matrix. So still they're working with Gaussian. Since they work, they're tricking us. Oh, because it's no, because you want it to be a conjugate prior for the covariance because you're using the covariance.
Right.
It also looks incredibly like, right, it could go through.
Oh, it should look like it. Oh, I mean,
Because
it's
it's kind of like the reparameterization trick, but made look much more complex than it actually is.
Yeah, so this might be a tactic of sigma shocking and hiding what is essentially Gaussian simulations. This is, I suspected as much, but
no, the key is the parameter tree, reparameterization tree, right?
Yeah.
Well, this is a Gaussian
Yeah.
of sigma square root. That's how you get a Gaussian of given sigma given mean.
Yeah. The only thing they added, it seems like, is this D-dimensional element. Oh no, that's also
Also,
this-
yeah,
that's exactly-
reparameterization. Yeah, it's only the A that they're doing, which is kind of like, I guess it's like how you map each mean to the input. It's kind of like how some people, what they do is they have data that's three-dimensional, then they sample a random matrix that's 3 by n, and then you have n inputs. That's what it seems like to me, where A is that matrix that maps it from, let's see, M to D. Let's see that. Or, yeah.
yeah. Anyway, curious.
Yeah,
No, yeah, and this is the first thing that had me raising an eyebrow, just because I wasn't familiar with this method of generating simulated data, but we can dig into it a little bit more here. So if they're generating this data in this fashion, they have this. They claim that this is a sort of a good representation, or provides us with a good representation of the actual spectrum of image data at CFAR 10, for example. So, right, this was a block of text that I didn't entirely parse when I first read it through, or even the second time. But basically what they're doing is that they are able to control the actual eigenvalues of this input-input covariance, which we saw in the Saxe work, by just choosing this parameter C and the columns of A. And they're able to control the distribution of the singular values, I believe, so that they follow this like huge spike around in terms of frequency. They follow this huge spike around some smaller magnitude, and then larger magnitude eigenvalues tend to be larger, so or tend to be fewer.
That's A, right? They do this is corresponding eigenvector, so that makes a lot of sense actually.
Yeah.
Yeah, see M eigenvalues. So they map it from M to D space, and then they expect that if you do this, blah, 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 you get M eigenvectors.
Right. So yeah, so I thought this was an interesting, this survey might be interesting for our own work if we're assuming that you have this certain constraint on the eigenvalues of your data, and can say this. So this would certainly inform how the rank would change of your learning potentially, right? If you are, so if their claims are that you're learning these dominant eigenmodes in sequence, these higher principal components, you would have a bunch that you quickly learn, and then you have this huge sort of cluster of lower magnitude eigenvalues, which dominate the space. a bit of a strange way of simulating data, but it would at least excited me for our range-based sort of dynamics potentially.
So the larger eigenvalues are to the right?
I believe so. This is this is, I believe the eigenvalue divided by the dimension of the data.
It's the variance of the C that they plot over D, which is the dimensions of the input data. So it's the variance of the of the principal component,
Right,
essentially divided by the input size.
which should be the singular values,
Yeah,
yeah.
exactly. Because what they show as like CM is sampled from a normal distribution with 0 mean, and rho M, which just means like for each eigenvector principal component, you have large M principal components. For each smaller one, you have rho M. So some of them are very high, like 0.51, and a lot of them are very small.
And yeah, a lot of them are very small. So,
Because I think D is just the input data, so that doesn't change, it's just a factor.
It's just a scaling vector.
yeah.
Yeah, I don't know.
And why display it this way? Okay.
Yeah, I didn't entirely, I thought,
Usually we display the curve and you can see that the top view and then it's just flat tail.
right, yeah, I thought it was kind of bizarre. I also am like skeptical of the fact that horses have this particular kind of spectrum. I mean, maybe they do, but I don't know. I haven't looked at CFAR in that much detail. What was that?
Frequency spectrum of the principal component frequency spectrum of horses.
Yeah, it's all very similar. So, so worth thinking about. This is the data. I imagine there might be some detail that I'm not entirely sure of. I don't know what Orchenko pasture distribution is. I think that's just jargon that they throw in there to sound cool,
That's like
honestly.
another name for normal distribution.
Yeah, right. It probably is another name for normal distribution. So let's get into some of the equations that they actually derive. So this is fairly straightforward. This is what I described already. So we have this split between the encoder and the decoder. Your encoder weights V and your your encoder weights W and your decoder weights V, which they are using to create the full reconstruction of the data. We have our mean squared error that we're optimizing. And this comes up with a fairly standard derivation of the gradient. It looks very weird, but this is just standard gradient for each variable. And they just use this G to kind of hide a bunch of stuff in this second equation. But this is just your normal gradient with really bad notation, in my opinion.
Their decoder formulation, it looks like it has skip connections.
No,
I don't recall them.
Because there's no G, there's no subscript for the G, so it seems like the decoder takes, you sum over every layer of the encoder for a G that doesn't change. Like
oh,
the
it's
same
just
G.
a 2-layer thing. It's an encoder with 2 layers.
But so they're saying sum over K, so you do the first layer and the second layer through the same decoder, that's what it looks like.
There is like encoder has 1 layer, just 1 matrix, and decoder has 1 layer, and nonlinearity is only applied to the bottleneck, and G is the nonlinearity.
And why do they sum over large K? This.
Oh, because that's how many hidden units you have. Okay, this is just to confuse
No,
you.
but I mean, yeah, why do they not, but how is it?
Oh,
so
what
that
they're
doesn't-
saying is, just
No,
another
yeah,
page.
okay, no, now I understand, but I didn't. why- okay, so
Yeah,
they just use only
okay,
one
1
reason
through
unit
K, and then here,
Yeah.
this is your
then.
X1.
Yeah, but they only use one ReLU unit.
Well, the G is applied here, right? G,
Right.
G.
No, I understand, but so they only use one ReLU, which is like at the.
Only in the hidden bottleneck, right?
Yeah,
here.
one, so that's one time, so I don't
One.
even know how nonlinear this actually is.
I have a question.
Yeah, well, what's up?
I don't know if it'll interrupt the flow of your presentation too much to do this, but if it won't, could you explain these equations to me like I'm 5 years old? Like,
5 years old?
no,
I don't know if a 5-year-old. Let's
Take
just
one matrix and multiply by a vector.
No,
and then
okay,
apply
like,
G
no, I
to
want to
the
know what all the
edge.
variables mean. I would like,
How about this? Will I'll explain it to you as if you're a 5-year-old who knows calculus. So.
No,
probably
So these are just your normal gradients for your weights, right? This is nothing
so what I
different.
really want to know is like, what do all the variables represent? I mean, like, what is D, what is lambda, and I guess,
So V and W are your weights on the decoder and the encoder respectively. Yeah, thanks for turning that up, Pavel.
Doesn't work.
It doesn't work.
Try it.
And then G here is your nonlinearity, and lambda is just a name for the output of the encoder, right? It's just this W applied to X and normalized.
okay.
So that's all that there is. I don't know actually what delta J here is. I don't think they ever define that in text. I think that's probably just
Oh,
nothing.
no, this is your AD. Vector.
Oh, that's the adjoint, yeah.
This is
Okay, that
the
makes sense.
adjoint and derivative of G.
Right, okay, yeah. So yeah,
This is I mean, this paper shouldn't be published.
What is the
I
COPA?
pretty wholeheartedly agree.
Why is
What is
this?
the COPA? Is that?
Oh, yeah, what is
Weight
kappa there?
regularization?
So kappa is a regularization parameter, I
Yeah,
think, yeah.
it's a weight regularization.
And eta is the learning rate or what?
Yes, yeah.
And they have individual learning rates for decoder and encoder or what?
And I
is
think they're
it?
tied. This is the same either, probably.
Oh,
But V and W is different.
Okay,
Yeah, okay.
that was nice. I appreciated that. What's D again?
The input dimensionality.
Yeah, it's the size of the data.
okay, well, but they call V and W is okay. W is the weights of the encoder,
Yeah.
V. is
Oh,
of
okay,
the
yeah, so they
decoder.
do have separate learning rates. That's what this is a
Yeah, that's what I'm
subscript.
saying.
I see,
Yeah,
okay.
but like this is overcomplicating simple thing.
Right, so this is, I mean, this is straightforward, but even in Saxe's paper, this is just, you know, the dynamics of the gradient so the dynamics of the weights, sorry, are just the gradients. Like you're not gonna get anything more complicated. So to be fair to the authors, this is just a first step, right?
Okay.
And then we get into the gritty details, which are a bit weird. Okay, so, and this is, I'm gonna need your guys' help, because I read this over a few times, and I'm not entirely sure I understand the full flow of how this reasoning works. So we are looking at these variables T, Q, and R, I believe are just the second moments of our I believe, so V here is just the weights on the so the decoder, right? Lambda is our
No, those
variable.
are new things. Those are what are the news?
Oh, this is new, but I think
It's
for Gaussian
something.
inputs drawn from 3.
It just seems like they redefine them as the same thing.
Right, yeah, so this is right here. So this is just redefined. Mu is just the decoder weights applied.
Backwards.
Yeah,
Transpose.
Yeah.
So now you're transposing the matrix and then applying. Yeah.
Right, so they are going to come up with dynamics for each of these expected value quantities. These the second moment between essentially the decoder weights and how they act on the inputs, the encoder weights and how they act on the inputs, and then the cross. The cross between the encoder decoder weights on the inputs.
They also kind of like are kind of, I feel like their assumption, or at least like they're kind of like thinking that that's maybe a solution, is like the matrices being exactly symmetric for the encoder and decoder, like the same matrix.
So they are. No, they're
No,
not.
no,
the
I mean
same.
more like they think that that may be the solution to the thing. Right?
Well, like you have X as the input and as the output, and the bottleneck is shared. So they're transposes of each other in terms of dimension.
Right, but then they take the V, the bottom one, R is like the V, the weird VK
Mu.
lambda, yeah, sorry.
Is that a mu or a mu? It's mu. Yeah.
New and you. Yeah.
Nu and lambda, so that is like the similarity between the two matrices, right? What they're doing there in the expectation of like R,
Right.
so they are,
It's kind of if you transform the output, like if you transform with decoder and with encoder, how they relate in the same space.
yeah, so that's what I'm saying, so they're looking at the similarity, but I think they probably assume that it's gonna be similar at the end, once you're fully trained.
And I do just want to mention writing this as, so they're looking at the eigendecomposition of the covariance matrix and taking out the, so this,
If this was linear, they would be identical.
Yeah.
Yeah, they would become identical. Those are just transposed. They will be orthogonal and identical.
right,
Although it's not weird to assume that these are also probably gonna be similar.
Mm.
Right, so this omega is just their way of rewriting the eigen decomposition for this covariance matrix. Right, so that's all fine. And then we will, so they're going to be looking at each of these quantities individually, and they focus in the bulk of the paper outside of the supplementary, they focus on this t variable. So that's what I'll be talking about most. I didn't honestly look through all the supplementary material. So there's like 10 pages of it. So let's see if we can follow through this derivation that actually describes the dynamics of this t, this expected, the second moment between the weights on the decoder, right? Okay, so this is just a change of variables that is describing the update of how the update between this second moment between the decoder weights would change if we apply the gradient. I don't think there's, I didn't step through the algebra, but I think it's just plugging in the gradient update to this difference here. And you're looking at the difference in the moments during training.
They probably made like 100 mistakes in their LaTeX before they got it correctly. With all the subscripts and like super.
Yeah, I bet this was a bear to
So
work with.
painful.
Yeah. This is like, I'm not a fan of like physics subscripting style, and this is like worse than physics subscripting style to me. It's just like, when I was trying to read my general relativity book, I just like hated my life, and still, yeah, this made me hate my life again. Right.
It's like they're already, I don't know, they already use linear algebra, right? So why don't you use linear algebra notation? What was that?
Oh, nothing. You can do hide floating controls.
How?
Yeah, more and then hide floating controls.
There we go.
Okay, I never knew this is possible. Thank you.
Great, okay.
What about the windows now with the bar? How do we get rid of
Now
that?
it's okay. I got it. Okay, we solved all our problems. We're
Yeah.
computer scientists here. We know what we're doing. Okay, so let's just say that they did all the algebra right. This is just plugging things in. So we had this value for t, which is the second moment, which is just applying the weights onto this eigen decomposition of the covariance matrix. All right, let's just say we understand that. And so this is the difference between, I guess mu and mu plus one, I would think are t at two different steps of training. That would
Like a batch or sample? Like are they doing
Must be
SGD, like
I think it has,
single,
so it's SGD, so but it has to be sample wise. I don't think this would work otherwise.
So next sample after update, m plus mu plus one.
I think it must be, I agree with Brad, that it must be sample. Otherwise you get into the whole issue of how do you do the decomposition correctly or the mean of things.
Right.
No, but there is no decomposition yet, right? It's
No,
just,
no, but everything inside of that, yeah, bracket is decomposed. It's a part of a decomposition, right?
No, this is just the partial derivatives. So this is
But they say the B, like the
you
T
can go back to the
thing
one slide.
is eigen decomposition, right?
So they take a derivative of this, right? Of the bilinear form.
Yeah.
Oh, quadratic.
Yeah, but I'm just saying, if you would also take the mean over this, that would probably be make it harder. No, the right part.
Yeah, slightly, but yeah, I mean, you will have sigmas everywhere.
Yeah, yeah.
That's-
right.
Okay, so then, got it.
Maybe they take the average dynamic, because once you have this difference, then maybe you can take the average.
But with respect to what they differentiate, with respect to omega?
But so these are different. This is a derivative with respect to
Looks like omega, no?
v.
So, but
It's a dot product, I think. I'm not sure.
Which,
it's a
That's
quadratic
right.
form, right? What they write there is a quadratic form, but in the previous slide. But they are writing it in
So
component form, so, and what is the variable of differentiation?
I think it's the next sample, it seems like almost. Or the next step, maybe?
Like with respect to what they differentiate.
Yeah, that I don't understand here because I initially thought that they were just taking the difference
The
here in
mu
this
and mu
t.
plus one. It's
Yeah,
mu plus one versus mu, so that's like step, yeah, I think it's like, and well,
like-
update at the step mu, that's what it reads.
steps equals S, yeah, see, and D is fixed, so mu plus one just means they're doing a step. For, I think for one neuron or something, that's what it looks like to me, or not, maybe
Yeah,
mu is the whole
there's
neuron,
steps.
and S is the step for one neuron, maybe.
K is a neuron, right? I thought, what?
No, but like if you do mu divided by D, then you divide it over the number by the input size, so that would be per. The output neurons are gonna be D's, the size is gonna be D. I think it's a step, because mu, see, I think it's a step.
I don't think they differentiate anything.
Delta V, like small step. not sure.
What are they?
No, I
summing-
don't think they differentiate anything.
What is
But-
DV then?
Yeah, but okay.
It's such bad notation. I'm like, I don't. I had such trouble parsing this when I was reading it. I'm still like not any more clear.
What's the sum of over tau? What are they summing over?
I think tau is, what was that?
Oh, no, I don't know, I think someone was.
I think tau is probably just summing over the
Data
spectrum,
set,
right?
look, it's over the data set. If you look at the top one, really,
Uh-huh.
Oh, yeah, it's summing over the
The
dimension.
dimension. not
Oh,
the
dimension.
Yeah, they do D for dimension.
yeah.
Yes.
Yeah, so that makes sense then, so they're taking the difference between the steps, I think, like the next step and the previous.
Yeah,
So
step.
this is the difference.
Just the difference, just like.
Yeah,
take the
and it's
difference.
between
yeah.
these second moments of these
Yeah, yeah,
decoder
yeah,
variables.
yeah,
All right, okay, so we kind of get that at a high level. All right.
At a high level, I would.
Yeah.
And for all, yeah, overall input dimensions.
Okay, and now they make this other step, so they talk about this order parameter density that depends on rho. And some normalized number of steps, and they can interpret this as a continuous variable as we, you know, have the energy
Dimensions
function
goes-
as dA goes to infinity. That last part I understand.
Why would
These
the input
dimensions-
size go to the?
Yeah, these dimension of
Well,
the data or the hidden limits?
The dimension of the data.
No, dimension of the data, yeah, why would that? ever
Like,
go
what
to
does that
infinity?
mean?
So that's this this
Oh, because
thermodynamic
it's the,
limit.
oh, yeah,
Yeah.
oh, yeah.
Yeah, that's the thing that Saxe does as well. I am fine with this.
No, okay, but it just seems like such a step, I mean, yeah, okay, it makes sense now, because they use the energy essentially to.
Right. Right.
I was like.
Okay.
Any data set that does that.
Interesting, okay.
So this is just a definition for a distribution, which is looking at this product between the decoder weights and applied it to some indicator function. Right, sure, let's say that that's a distribution. So they can use this to rewrite this update for V, which was in equation 4, which I don't know if I included actually. Crap, I should have put that in here. I think it's one of these. I think it's this one.
I'll tell you.
Yeah, can you tell me?
Yeah,
Equation
that's the
4.
14.
Yeah, I think this was 4. I think I just missed the number.
Okay, I was forgetting to put it in, is like.
I did read the paper.
It's similar to this one.
Yeah, no, I'm pretty sure this was it. I did read the paper, I swear.
No, it's just funny, because you're like, oh yeah, it looks kind of like this equation.
No. So they insert this equation here into this continuous time variable, and now compute the expectation over some fresh sample X.
What is that notation of K mapping back and forth between L? What does that mean?
So that I don't understand. It's K if and only if
I'm
L.
gonna take this out of my
If and only if.
Yeah, K map L. Okay, well, yeah, interesting. Well, the most
Well,
important part, I think, is the gradient update part. I don't think the K, I mean, I guess it's important.
So this is what they come up to. This is their derivation. And they claim that this can be used to say that Right, I'm trying to parse exactly how they say this. I don't want to give them credit for what they don't do. I don't entirely.
I keep using the double-headed arrow.
Yeah.
So in my opinion, they Sigma shocked the reviewers to hell, and
No one understood.
no one understood
No
it.
one
They thought it was
yeah.
crazy. They had a lot of supplementary material.
Yeah.
Let's skip over this for now, and maybe we can come back to this and try to dig into the details again. I could not parse this. It's beyond my ken, even as a math guy. I just like, this is not very clear.
Yeah, it's so not clear.
But I also feel like the outcome to me seems almost too trivial. Because if you just use a ReLU, you would just expect it to not pick up on outlier principal components from an intuitive perspective anyways, because the only thing that you're doing is it's linear, except if they're set to zero.
For that shallow depth.
Yeah.
Yes, like it
Yeah,
doesn't
only
have
for the
enough
most
room
important-
to keep splitting
Yeah,
into the.
exactly.
So
all it
let's-
does
It's
is
just a
splits.
sparse PCA almost, where you just set the least important ones to zero.
So I agree, and I think that applies to all their results after this one, but they do actually look at sigmoid autoencoders as well.
Okay.
So at least from their figures, so this, to just interpret this for you, the curves are analytical predictions using whatever equations they derived for the actual trajectory of learning during training. And the crosses are numerical estimates from simulating this data. And it seems that even for sigmoidal networks, they're able to perfectly describe the trajectory of learning. And it has this, let's go panel by panel. So they first are predicting PMSE. They have right, some just exponential decomposition, then power law decomposition, or not decomposition, decrease, decay. And they're able to perfectly describe this two-phase of learning. Now, this first plot doesn't have any numerical estimates in it. What that means, I don't know.
Do you use your mouse? Yeah. Yeah, okay.
Yeah, this first plot here on the left.
What is random and aligned?
Where?
That's the two lines.
Oh, these are random inputs, randomly perturbed inputs, and I don't know what the aligned inputs were. This is probably mentioned in the experiments, and I just glossed over it.
And what are the colors in the other ones?
So these are,
Why don't they have legends?
sorry,
Why don't they just have a legend?
they do have one, but all it is these are the trajectories I imagine for
The two scaling constraints?
so these are the ones, I don't entirely understand this figure, but these I think I do understand. So these are the norms of the encoder and the decoder weights. And they are able to, again, the curves are the actual analytical solutions, so obtained from
Before
integers.
you switch, you will read this sentence. This allows sigmoidal network to remain in the linear region of its activation function and
Yeah,
to
that's what
achieve
I'm saying.
this.
Yeah, that's what I'm saying. It's like cheating.
Well, but they say, but what they're saying though, so is that even for sigmoidal activations, this happens. They're not saying that it's their data. Well, I think it might be their data, but
Well, it's also because they use one layer, I think. I mean, it really is simpler to get the linear decomposition if you just have a single, like.
right, even with the sigmoid activation.
Well, I mean, that doesn't make the results worse, but I just like it, I feel like it's a lot of math. And it's good that they've achieved this performance, but more like it's a lot of math to kind of point out the obvious to me. Not to say that it's not valuable to do so. I mean, it's important, but I'm just saying.
Yeah, I think I also I agree with Eli. I am not entirely seeing. So it's cool that they have these equations that exactly describe it, but it is it should be trivially PCA, right? That's
Well, yeah, so I think the description of the gradients is interesting in terms of dynamics. I just don't see how this like idea of like, oh, it's doing PCA is such like a new idea. I mean,
Yeah,
that's
yeah.
really kind of what you would always expect. I don't know.
yeah.
For a single layer autoencoder.
I would say that it's an expectation.
I mean,
1989, color, and I put the first author. proof. Or
Yeah.
something.
So I think they do actually cite that work, that particular work, that 1988 or 1989 paper.
No, color was something else, but yeah, there is a paper.
But yeah, and all of their results kind of center around this idea that we're one by one estimating principal components. This one I didn't find as interesting because they don't show any numerical prediction for it.
But wait, so you said that essentially David Saxe in 2003 or 8 has already showed kind of that we're doing this principal component stuff for the
So
classification.
he did it for a regression, and he
Okay.
was looking at the. So let's look at this figure. This is one of my favorite figures for Saxe, and this is they're actually estimating the dominant modes, the initial
Right.
principal components in the input-output covariance.
But that's why I'm saying that this is on top of the paper that Sergey mentioned. It seems like it's still important to show, and I'm not saying that this should work, but it feels like a little bit like, you know, they just do the exact same thing, but they just add the decoder, and then they're like, oh yeah, it still does that. It's kind of like, yeah.
I do agree with that analysis. When I first saw that this paper got accepted and I saw it was on dynamics of autoencoders, I was like, oh shoot, do they do like very deep autoencoders with like a lot of nonlinearity? Do they do variational learning? Those would be all things that I think would be novel and interesting, but I do think that
I don't
this
even
is just a
think of
rehash
it
of
as
Saxe.
So I posted the paper with the proof, 1988.
Yeah.
Also, not the one, not the authors I thought about, but yeah. Auto association by multi-layer perceptrons and singular value decomposition. So they proved that. Yeah.
But so this figure, so this is what I was getting at, where they say that if you break the symmetry, the rotational symmetry between the neurons, it is the autoencoder exactly does PCA.
It's interesting because I don't know, Sergey, if you remember that paper by what's his name? He used to be in our lab, but he's now at Apple. He went from Microsoft to Apple.
Apple, I was gonna say Devin.
Devin, yeah, Devin is at Apple now.
Is he at Apple now? Oh, I didn't know.
But so
He's
he,
jumping,
yeah, he has this restricted Boltzmann paper,
Yeah,
right, with single layer, and then he does like L1 norm. But so now the more that I'm looking at this, kind of sounds like.
Well, we didn't do theory
PCA.
as much.
No, I know,
We
but
didn't
like
do
now
that.
that I'm thinking of it, it seems a lot like PCA probably, the restricted Boltzmann.
Ryan, right?
Yes, would this suggest that then like a doc-to-vec model, like the simple models that were designed a long time ago, that those would essentially be PCA as well? Because doc-to-vec models, they have, you know, the single layer, and then they have the single hidden layer and the activation there, and then the single outer layer. And so would it be basically doing the same thing
I
as
didn't know
PCA?
specifically the doc-to-vec and word-to-vec. I thought they had some other stuff that would make it probably not.
Word to it is exactly
Yeah.
SGT.
Okay,
Yes,
Yeah.
it is exactly SGT.
not doc-to-vec then, but yeah.
Yeah,
Okay.
I don't know how doc to vec works, but word to vec is PCA. Yes.
Yeah,
And there are like, I mean, the way you train it, blah, 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 adds some complications, but it's practically a PCA.
Yeah.
It's what is it, latent LSA, or there's latent semantic analysis is very similar to that, and GLOV kind of exposes that even further, because that's what it does, SVD of the frequency, whatever matrix that exactly what they use.
yeah, I mean, it makes sense to some
But,
extent, right?
there is one difference. When we're using linear algebra to solve, the only thing that, let's forget about all neural stuff, just the linear algebra. The only thing that Saxe showed and what they're showing and what this 1988 shows is that stochastic gradient is, well, I'm maybe over committed to 1988. I don't know how they showed it, but SGD gets vector by vector. When you're solving SVD, you don't have, you can use it by Gibbons rotations or something like that one by one, but you don't have to recover one by one. You can recover it once, or you can use different algorithms. SGD realizes one specific way of finding PCA, the principal components, one by one.
Yeah.
So the largest is recovered and then subtracted. And then it's like,
To me, it's kind of like similar to how they try to add more data to original PCA. Like there's a lot of algorithms where they first do PCA on a training set, but then when they get new data, they can continually keep adding to it. That is essentially the same, which is kind of like SGG, but.
They do talk about that online
Yeah.
learning component in the supplement. I didn't read it at all. That'd be interesting.
Right, because that's like a very common way. So Mark Davenport in the EC department does a lot of research on that kind of stuff. And it's interesting because it feels very similar kind of to what they're saying this model is doing too. Because you first find like the largest components, right? If you keep adding like subjects essentially, let's say to a PCA component, it would make sense that you first find the largest ones and then slowly start to get to the smaller ones as well. But anyway,
I don't know, yeah, maybe, for example, some other learner would be first filtering out the noise, not, well, is that equivalent, like,
yeah,
going from the high frequency and removing them?
Yeah.
For example, I don't know, like, there could be different, there is some information in there, right? But that, oh, they're learning this way by low vision and then adding frequencies, rather than
Yeah.
noisy and then removing. So they start low pass and add high frequency components as they learn.
well, also PCA implementations are often not fully like analytical. I think they do like some, because to get the eigen decomposition, it's sometimes hard because matrices are not always able to be eigen decomposed. So for example, in sklearn, they do some sort of like randomized initializations and stuff to help with the actual decomposition.
You can always do PCA though, even if it's not eigendecomposable, because you're just doing it over the covariance matrix, which is always eigendecomposable.
Yeah, but so the way they normally do it, because you need to pick the eigenvectors. There's an iterative way of doing it, I think, that is most efficient. That's what I mean.
I think something like that always exists.
Yeah,
No,
that's
true, but they do it often in an iterative way. That's why you need to give a seed to the sklearn, for example.
Yeah.
That's what my
Yeah.
professor talked about a lot.
You don't have to do it in an iterative way.
You don't have to, but
numerically,
people often do.
but you can choose the lambda and it will be always invertible and you'll find the component.
No, that is true.
But I think thinking about, I mean, this is relevant to our work, thinking about those iterative methods and how we can sort of most efficiently get this same behavior. And power durations, they are essentially a way of estimating dominant eigenvectors, eigenvalues first, and then just subsequently getting the higher frequency modes. And it's just a question of what's the most efficient way to do this now for if we're doing rank reduction. And we have this perspective from auto differentiation where we want to exploit it, come up with a nice trick to do it more efficiently.
Yeah.
But so interesting. That's the long and short of this work. I think we've gone over. So this was you've been mentioning this whole time that yielding exact PCs is a little bit of a big thing to say for autoencoders in general. And the simplified network, I think, maybe is not getting at all of the detail that would happen in practice, in my opinion. But yeah, I think an interesting paper, a little bit opaque and probably more simple than they try to let on, and that's probably where they got accepted, in my opinion.
Because I think I saw a paper that was on variational autoencoders, the deep ones, and they're more empirical, and they're like, it first starts in the direction of PCA components, but then slowly starts to move away from it as it learns more. Like it starts to use the nonlinearities. That's also based on initialization, obviously, whether you're in the linear region of your, starts in that direction, but then slowly starts to use kind of its nonlinearity at some point. But that's for deep ones, so it's very hard to compare that to this.
Yeah. But people are doing this work, and it's at least interesting that we're seeing more and more of this kind of analytical attempts. So I was happy to see it. I was unhappy that they got in and I didn't, because I think they deserved it more.
That's always the case.
Well, they did one data set. We got lambasted for doing. I think we had 3 data sets or something. We got so much flack for it because they were not large scale, quote unquote. And CFAR10, while more large scale than say an MNIST or one of the smaller time series data sets we were working with, is still not large scale compared to ImageNet. So it's just like, it's reviews are a gamble a lot of the time. Sometimes they get people that hate your work for no reason and just want to be mean to you.
That's like face control, a friend of all, he's a person from the start. They look at the paper and like, oh, it has a lot of, I don't know. But another kind of depressing thing is that we don't really have good math to analyze nonlinear phenomena anywhere. We linearize,
Yeah,
and like this is like, oh, we can do linear, let's do linear, okay. And that's on lots of papers in physics, when they study nonlinear effects, they're on like, piecewise linear, let's just look at the linear.
yeah, the whole field of PDEs is about linearizing stuff until it works, and,
Yeah. But
I thought this paper, I mean, my comment at the beginning in the chat where I was basically asking about the textbook, I mean, was I read both of these papers. My eyes went through them at least, and I would have found the material extremely interesting if I could not overcome the sigma shock. But I think the only way I'd do that with a tremendous amount of context. And
I do think that the story is likely simpler than they are getting on. And there is a simpler story to tell with clear notation.
I do think David Saxe does a better job. It's still hard. You need to like stay awake to like make sure that you understand every sentence. But I feel like David Saxe is a little bit more. It's also very notational heavy.
I mean, Andrew Saxe, is David Saxe someone else?
Sorry, yeah. Andrew Saxe, yeah, sorry.
Yeah, I wasn't
But
sure.
it's definitely easier to get through a little bit
Yeah,
because they do also explain it.
I also think Saxe does a much better job. He starts with a very simple example of a 2-layer network and analytically derives everything. And it's very clear if you understand linear algebra, how everything works. There's some like changes of variables and stuff that aren't very clear initially, but yeah, I think this paper, could have done better by, just cleaning up their notation for the love of God and being honest about sort of the extent of their claims, maybe. But you got to advertise. I don't fault the authors for doing that. I think, and congrats, Maria, if you're here in the call. So that's it for me. Do we have anything else we want to talk about? Read this paper, or
anyone online has any questions? Can you again?
we're almost out of time. So
Why did you stop the recording?